Welcome everyone. My name is Jan Drgonya, and in today's tutorial, I will show you how to use system identification with neural networks in NeuroMANCER scientific machine learning framework. After today's video, you will learn how to use differential models such as neural ordinary differential equations or NODEs, or neural state space models or NSSMs, incorporating prior knowledge into the architecture and loss functions and use them in learning dynamic system surrogates given time series data. First and foremost, we are working with the NeuroMANCER scientific machine learning library that is open source at GitHub that you can find on this webpage. And we assume that you have installed NeuroMANCER and everything is working well. If not, please check our introductory video with installation instructions. And today I will walk you through the examples in the system identification folder. When we are dealing with dynamic systems, we typically assume some system that is changing with time, and it can be formally defined as this non-autonomous, partially observable, nonlinear dynamic system given by some differential equation f that is mapping your state space into the derivatives. You can have some controllable inputs or disturbances that perturb the system, and you may have partial observable system with this output mapping G, mapping your latent space into the observable space Y. Typically, we are solving initial value problems where we provide the initial values of our states and sequences of the controls that perturb the system and obtain the rollouts or n-step ahead predictions of these dynamic systems. In reality, we gather time series data that come in input-output pairs given in a dataset S. So we have these tuples of our inputs and our outputs at time t and consecutive time shifts with some temporal gap, a delta that is being called sampling rate. You can have also sampling rates that are not fixed. You can have irregular sample time series data. That's a more challenging problem, but for now we assume fixed sampling rate. And you have different rollouts or different batches of these trajectories, so they can represent rollouts with different initial conditions or different operating scenarios. And this is indexed by the scenario I that represents essentially your batch in the data set. And here, our primary objective of this physics-informed or physics-constrained system identification is to construct structured digital twin model that learns the unknown dynamics of the given system by provided only this limited time series data and some prior knowledge about the system. In our framework, we support different kinds of dynamic system that can be just simple autonomous system that is mapping your states to the state derivatives, or it can be non-autonomous systems dependent on time as explicit input variable, or fully non-autonomous system that is perturbed by some system input. What are we doing under the hood? We are representing this as a combination of black box or white box components that is typically being called universal differential equations in the Julia community, or can be fully black box model like neural ordinary differential equation or neural state space models. So before moving on, it's important to note that there are two dominant neural ODE packages that are freely available. The first one is differentiable equations library developed by Julia community in their SciML ecosystem. It's probably the most powerful differentiable equation library out there. The second one is the TorchDyn, which also builds on PyTorch ecosystems, the same like NeuroMANCER. And these both packages are well documented and has been well established in application-based literature. But where the NeuroMANCER brings novelty and contribution is that we systematically combine constraint optimization practices and control theory in one unified package. So once you train your neural ordinary differential equations or any structured digital twin model, now you can use it in a constraint optimization setting as a constraint or in optimal control setting as a dynamic system. surrogate that represents your differentiable model. So on a high-level conceptual basis, we can integrate the different types of system identification objectives and soft constraints or hard constraints in their architectures by various means. I will show you in the code. If you are interested in the high-level mathematical formalism, you can read our README and associated papers. But essentially, there are two ways how to embed prior knowledge. First one is to do it through Lagrangian loss functions or soft constraints, where you are basically having multi-turn objectives with different weighting factors that each penalize different things, like whether it is reference tracking or like smoothing your trajectories or having some inequality constraints or having some physics regularizers like you would do in physics-informed neural networks. The training algorithm conceptually is very simple. So you need to have some time series data set of sample trajectories. You provide some architecture of your differentiable twin. It's neural ODE or state space model or any custom defined dynamic system surrogate. You provide this physics-informed loss function, and you provide with the optimizer that in our case is based on PyTorch, a gradient-based optimization. And now you differentiate this system ID loss function and backpropagate these gradients through the digital twin model. And the second way how you can embed prior knowledge is actually architecturing the digital twin model. You don't have to have just fully black box neural network over there. It can be very structured and embedding sparsity, positive definiteness, boundedness of your eigenvalues, and many different things that can be very useful as inductive priors for application domains you know something about. And that's basically it in terms of the high-level algorithm. And now we can switch to the code. If you are interested in using it in a practical setting, I will start with simple duffing parameter estimation that can be found in our system identification examples, duffing parameter. And it's one of the simplest examples we have out there. We are going to estimate one parameter of the duffing ordinary differential equation. So instead of having black box system identification, we know the right-hand side of our ordinary differential equation. We just don't know the parameters. So we are starting with the imports. Our core import is PyTorch, some NumPy for generating data. Slim is our structured linear maps library, which we are not really going to use in this particular example, but you could use for some linear algebra factorizations of your weights in neural network components that can act as inductive biases. We will import PSL, which stands for Physics Python Systems Library. And we will use this one to generate our time series data. And everything else is our core NeuroMANCER imports that will build your computational graph, your digital twin model, physics-informed loss function, and aggregate everything in differentiable computational graph that can be trained given data. Okay, so we start with generating some raw data set that corresponds to our ground truth model that we want to imitate or like learn the digital twin of. In this case, we are using Python system library where we have defined ODE system. So very quick sneak peek into PSL. It's a minimalistic library that provides you with high-level APIs for defining and solving ODE type problems using SciPy library. It's a rather straightforward setup. It's very minimalistic, doesn't require a lot of dependencies. And essentially what you can do, it provides you like with the catalog of predefined canonical dynamic systems like this Duffin oscillator that you can simulate and quickly obtain some time series trajectories in this case, and plot its phase trajectories that can act as a benchmarking for your system identification model. So we have a long list of library of simpler and more complicated dynamical systems, including network systems, autonomous, non-autonomous dynamic systems, or some data sets from real world. So this can be used as a benchmark library for any nonlinear system identification. So that's what we are using in here. We define the system, we simulate the system over predefined number of time steps, and we obtain some raw data set that comes as a dictionary of NumPy arrays. We expect different types of keys for capital Y, which stands for observable space of outputs. Capital X stands for latent space, and some systems may have explicit time information, like in this case is non-autonomous system, that will be automatically processed later on in our data loaders. But this raw data set can come from any means. You can load it up from your computer, from the CSV files, or you can just parse it from the URL. Doesn't really matter. Okay, so once we have the raw data set, and you can visualize the trajectories that we are going to use for training. So as you see, we have some sampled trajectory with one initial condition. So this will be very simple parameter estimation. And we will use only portion of this trajectory for training, probably like this portion that will be used in the learning algorithm. Next step, we are going to create some interpolator of our time for our system integrator. So this is necessary when we are solving OD types of systems to basically fill in the gaps for which we don't have explicit measurements. But the interpolator is a relatively simple class that basically provides you with filling up the missing points for the time series with fixed sampling rates. So that's what we will use later on. In the next step, we create our custom PyTorch data loaders that use NeuroMANCER data sets. And how do we do that? We provide with this raw data set of observable outputs Y and latent space X, and if we have an autonomous system, then explicit time information. And we provide desired number of time steps we want to create at chunks of the data set over these n steps. So we go to the declaration on usage of this helper function that creates these PyTorch data loaders as an open loop sequence dictionaries. So the dictionary will map the variable name given in string, that's the key, into specific torch tensor value data set. So everything in NeuroMANCER is based on higher level symbolics, where we represent variables with their corresponding names in strings, and they carry tensor values as the means for forward propagation. Okay, so the data is a raw data set that expects some canonical keys that will be this X or Y or U if you have input action. And we provide number of steps. That's the length of the window that will be used for batching of these chunks of trajectories. And what you essentially do, let's say you provide trajectory of 100 time steps and you provide n steps equal to 10. So you will cut the trajectory to 10-step long horizon sub-trajectories. So you can have like different batches. But you can do it in multiple ways. You are just going to cut it as a sequence of continuous n steps, or you can cut it as a moving horizon when you are just shifting your horizon one step ahead, and you are taking subsequent 10-step ahead horizon. When you're using moving horizon, you are basically like having the smooth transitions between your n-step ahead trajectories, and you end up with more batches. If you want to save some compute, you don't have to use moving horizon, but you will essentially carry like less information during training. You can normalize your trajectories. That can help, especially with the data set that are not very well balanced. And you can provide different split ratios, that is percentage of data that will be used for training, development, and test set. By default, we are using 1/3 for training, 1/3 for development, which is evaluating the performance and selecting the best model, and then for test, which is independent data set. Number of workers by default is 0, and is essentially how many subprocesses they will be used for data loading in the PyTorch data loader. More about that, you can check the definitions in the PyTorch data loader arguments. And the batch size is how many samplers per batch to load. By default, we are using full batch, but you can change this to any like mini batching you would like. So what happens in the sequence data loader is like you normalize the data if you have some if you select some normalizer function, then we split the sequence data into train, dev, and test set based on the split ratio. And after we are done, we have like these 3 raw data sets. We are going to instantiate 3 NeuroMANCER dictionary data sets that will expect these keys like outputs, inputs, and states, carrying NumPy array values, and they will parse it into Torch tensor values and basically do this n-step ahead long processing of different batches. What we will end up with is a dictionary with string values for the variable names that will come with tensor values of 3 dimensions. First one is how many batches we have, how many sequences of trajectories. Then the second dimension is n steps, how long is each trajectory in individual batches. And the third dimension is what is the dimensionality of the actual variable. That can represent some physical quantity like temperature, pressure, velocity, or speed. Also, one thing which is happening automatically in the sequence dataset from NeuroMANCER is the creation of past and future trajectories that can be utilized by the high-level problem formulation, because very often we have some kind of system estimator that looks in the past, predicts the current initial conditions, and then we want to predict for a future. So that also happens automatically. So once we have this train, dev, test NeuroMANCER dataset, we can also obtain the full sequences by calling the method getFullSequence, which essentially collapses all the batches into one and creates n steps ahead trajectory that is like continuous trajectory of the raw dataset. That could be useful for plotting or for testing. And once we have these data sets, that's the train data, dev data, test data, we are going to instantiate PyTorch data loaders with specific arguments for number of mini batching and number of workers. And that's what we return in get sequence data loader. For practical use of the library, you don't really need to worry much about it. It's only when you would like to have some kind of custom data sets for data pre-processing, that's where you would need to go inside and investigate what's going on. So NeuroMANCER will process the data for you. And once you have the data pre-processed, now you can actually start articulating your architecture of the system identification problem. we typically start with the system estimator. We have some observable space, which we want to map into the initial conditions of dynamical system. That doesn't necessarily need to be fully observable, but in this case, the simple example, we are assuming fully observable systems, so we just define this estimator that will basically take what it sees in the observable space and parse it as the initial conditions. So there will be no transformation over there. Estimator is essentially mapping these observables into the initial conditions. And it represents NeuroMANCER class that is a component class. So when we go to the declaration of its parent class, it's a NeuroMANCER component. What is a component? Component is one of the basic abstractions in NeuroMANCER that essentially define a symbolic mapping between input and output keys that are list of strings. So input keys represent string values of our input variables, and output keys represent string values of our output variables. So that's how we have this wrapper of the symbolic expressions on the top of torch NN modules. Okay, so that's what is estimator, and as each component, it must have input keys that are going to map to the output keys. So that's what is in making it as a component, symbolic component in the NeuroMANCER differentiable graph. The second important component would be actual dynamic system. And we start first by defining NN module class that is mapping tensors to tensors. This can be some black box neural network architecture that is mapping specific input size to the output size, and you can have defined different hidden sizes. So if I would go to this definition, it's just simple multi-layer perceptron that is consistent with our block interface that is allowing you to have simple Keras type definition of your neural network modules with predefined parameters for activation function, different parameterizations of your weights, whether you want to use bias or not, what is the size of your nectar, etc. So these are very simple abstractions, but you could use some custom architectures like input convex neural network, positive definite networks, or implement your own right-hand side architecture. So here where the structural assumptions come in. More powerful structural assumptions for dynamic systems are represented by differential equations. And in this case, we are implementing what is called universal differential equation construct developed by the Julia community that essentially defines arbitrary ODE type system that combines white box principles and black box principles in one systematic way. So our base class is defining the right-hand sides of the arbitrary ODE functions, and that can be mixed matched. So you define your own ODE equation, and examples include like this Duffing parameter where we define a set of trainable parameters. Some of them can be fixed or not, and you define your right-hand side of your ODE. So this is parametric ordinary differential equation. There are no black box components. We are going to learn only one parameter in this example. That will be the omega over here. So what will be the influence of your time on this ODE? More complicated examples can include the hybrid ODEs or universal differential equations when you will actually systematically combine the black box components with white box structure. So here we have still two-dimensional system, but now parts of the systems are fully black boxes. This can be any neural network architecture, any deep neural net, multi-layer perceptron, or recurrent neural network, whatever is good assumption for your case. And it's fully compatible with our blocks or in neural networks. So what you implement in blocks, like input convex neural network, you can go here. Okay, so that's for defining our ODE type system. And it's just a PyTorch NN module. It's a callable. It represents the right-hand side. To make it differential equation, we need to provide a system integrator. In our case, it will be Runge-Kutta 4. So you provide this right-hand side of the ODE you want to integrate. You provide with this offline interpolation of your inputs, in this case, the explicit time, that will account for the missing points in the integration and the integrator step. So if we go over here, the Runge-Kutta equations are defined over here. Over here is the very standard integrator. For those of you who are not that familiar with ODEs and how integrators work, I strongly suggest you to check some Wikipedia pages or some ODE learning material. It's basically how you numerically solve continuous time ODE type systems. So that's what the integrator does over here for you. It allows you to obtain these discrete time solutions that we are going to use for training this universal differential equation. But this is still mapping tensor values to tensor values. How do we actually make it symbolic? Well, for that, we are going to wrap it in our ODE non-autonomous class that comes from the dynamics systems, and it's again a component class. So we provide with this latent dynamics and the observable output model, which in this case will be simple identity, and we provide with what we call input key maps that are mapping some canonical variable names that are essentially expected variable names into whatever you really want. You can rename the canonical variable names such that it fits your computation graph. And you can provide some extra inputs if you want. But if you show the dynamics model, it will give you a representation of what it's actually doing. It expects future trajectories of y, it expects initial conditions, future time steps, and it will return some regularization error of the class and the predictions of the latent space and predictions of the outputs based on this Duffin equation that is solved with Runge-Kutta 4. So what is actually happening inside is the following. The ODE non-autonomous systems is expecting these two default output keys, initial conditions and future trajectories of our outputs. They're not actually being used for prediction, but only for inferring the number of time steps to roll out the trajectories, because we are dealing with dynamic computation graphs. So instead of having some extra argument you need to hand over, the length of the rollout is inferred from the data provided. So it can be very flexible. And you have some default output keys that are latent space, output space, and regularization error. As I said before, you can use some extra input keys if you are dealing with non-autonomous system that has disturbances, control actions, or explicit time. You can provide different variable names for each of them. The online flag is whether you use online interpolation or not during the inference, and the forward pass essentially performs the n-step ahead rollout of a given dynamic system. So I'm not going to go into much details, but this FX over here is the Duffing ODE solved with specific integrator like Runge-Kutta 4. So that's what is happening under the hood of the dynamics model. which is essentially a symbolic wrapper and the rollout generator of the ODE. Now, when we have these symbolics, what can we go? How can you go further and create objective values and constraints in nice mathematical language inspired by constraint optimization community? Well, for that purpose, we create this variable class that is another symbolic expression that can point to the variable names in the data set. It can point to the variable names in the input-output space of the components, or they can be created as a composite variables of the previous variables. So here, my y hat is the variable that will be looking in the dictionary of tensor values for this specific key to provide you with the tensor values that correspond to the predictions of the dynamics model. Y will be looking for YF, but I could also create initial conditions that first I need to check the estimator output keys. Okay, so the estimator output keys expect it will return X not fully observable. So, and it'll be in the first position, so I can pick it up like this. And I can wrap it over here in the variable. Okay, and I call it X naught. Now you created new extra variable in this command line setting that can be used in the definition of the objectives or constraints. So if I would like to create objective, I would say, okay, this needs to be equal to 0. And now I have objective term that will do that for me. Or I want to say this initial condition needs to be always positive. It can go like this. Or I can do comparator with different types of variables, and I can say this needs to be larger than y. Okay, so that's the way how you define the variables and define the objective terms and the constraint terms. But you can also define the variables in a composite way. So here are two examples of creating finite difference of variables. So we can do slicing because this variable will actually point to the three-dimensional tensor, where first dimension is number of batches, length of the individual trajectory in each batches, and the space dimension of the variable. So what we are doing here, basically, we are slicing the variable and creating a finite difference of our ground truth outputs and finite difference of our prediction models. But you can also go and create any custom variable. So let me check y. Okay, this is NeuroMANCER variable, but also y power to 2 is the variable. So it can be really any arbitrary computational graph. You can even combine this inline definition variable, and I will call it x. Okay, so this is a still variable. And I'm going to assign it to new variable. Let's call it p. And it's a variable that has some display name, but it will have unique key, which is the identifier that is actually being used for tracking the computational graph behind the hood inside the NeuroMANCER problem forward pass. You can also show the variable, and now you visualize the computational graph, symbolic computational graph that constructs this variable. So you have this yf on power of 2 plus 5 plus x, and this is your variable. You can go even further and not only use this operator overload approach when you use standard operators, but you can use any PyTorch callable, large sum p creates also a NeuroMANCER variable, which is a very fancy way of creating arbitrary custom-made symbolic computational graphs with PyTorch callables. So let's call it PS and show PS. Now you basically expanded this symbolic computational graph with extra node that represent PyTorch callable. So it's a very flexible way of defining symbolic computational graphs that goes on a low level. The components, like this dynamics OD non-autonomous class or estimators, are wrappers for specific architectures in our framework that are high-level symbolic representations. So very often you may have some architecture trained in a standalone application that is not symbolic and you want to wrap it, you can create your own symbolic wrapping components. But if you want to go really low level, define your variables and use them in constraints definition or objective terms definitions, then you can go to the variable class and combine them systematically together to generate complicated, complex symbolic computation graphs. So that's what we are doing in here. We are defining some loss functions. This one would be finite difference loss. So we want to say that basically the first order finite difference of our output model needs to be somewhat close to the first order finite difference of the ground truth model, which works very well when there is very little noise in the data. And this is standard reference tracking loss. And everything will be automatically computed by the NeuroMANCER problem that will aggregate everything in one scalar valued loss function through the list of objectives and list of constraints. So you could go on and on. You could say constraint 1 equals that y hat less or equal 0. So you want to penalize that your predictions are always positive, and then you would hand over this constraint, the list of constraints. And you can go on and on. You can even like make this programmatically, create different for loops. And you bring everything together in this penalty loss. The penalty loss takes in objective terms and constraint terms and aggregates them. So if you want to see like behind the scenes, you would go to the loss.py and check different types of aggregators we have there. So it's all defined by the abstract class aggregate loss that calculates your scalar valued loss function that will be actually used for training, depending on different constraints, objectives, terms that you define. Currently, we support 3 types of loss functions: penalty, barrier loss, and augmented Lagrangian loss that you can use, and we are working on expanding this further. So this penalty loss or any aggregate loss will be used together with the components, the symbolics, to create computation graph in the problem class. So what happens inside is that you are constructing a constraint optimization problem and represent it as one differentiable forward pass that can be used using standard PyTorch autograd. So this is similar in spirit to the NN sequential module in PyTorch. However, by concatenating the input-output dictionaries, we are creating custom symbolic computation graphs that can represent arbitrary directed acyclic graphs. And in addition, the problem will calculate the forward pass of this computation graph and provide you with the scalar value loss function via this aggregator for backpropagating in the gradient-based optimization. So I'm not going to go into much into details into internal mechanics, but the forward pass is very simple. We obtain the step, which is essentially for loop over our components. These are the high-level symbolics on some neural net or any callable architectures like neural ODs. And then we calculate the loss, which is, again, aggregator of our low-level symbolics with variables that create constraints and objective function terms. Okay, so once we have this problem, it has also like this neat representation that will quickly provide you with the summary, what it does. So it has components, and you see like the first component is mapping YP, it's fully observable estimator. It's mapping past output trajectories into initial conditions and some regularization term on the internal components. The dynamics is mapping the future trajectories that are given for the inference of the n-step ahead rollout length, given initial conditions from this observer, and explicit time, because it's non-autonomous system, to generate latent dynamics and output dynamics trajectories, and comes with regularization terms. There are no constraints in this problem, but there are two loss function terms. So the regularization term I didn't really mention, but is essentially a method in each of our components that represent a fancy way, or like a more convenient way of making local regularizations being visible on a high level, symbolic level. Okay. For even more intuitive representation of the problem, you can do problem.plot_graph. And now what you see is a computation graph of this on a high level symbolic level. So we have some data set that is automatically generated by NeuroMANCER dataset and PyTorch data loaders that provides us with some past trajectories for a fully observable system dynamics model, and it generates some initial conditions for the dynamics model that is a symbolic wrapper of our neural ODE system integrated with Runge-Kutta integrator. The explicit time is provided in the dataset as well, and the future trajectory here is used for dynamic computation graph, defining number of steps into the future, and it's also used in the finite difference loss of analyze the dynamic output trajectories, and is used for reference tracking loss. And these two objective terms are being aggregated in scalar value loss functions through penalty methods. And now you can backpropagate these scalar values through the computation graph and update only the trainable parameters that require gradient. And they can be in system dynamics, they can be in the state observer, they can even be in the variable class, and you can learn the boundaries of your constraints, etc. So this is a very flexible framework for defining physics-informed constraint computational graphs. Use gradient-based optimization for data training. Okay, so once we have the problem and everything is defined on the architectural side, we can go ahead and train this model using standard gradient-based optimizer. In this case, it's ADAM. You can use ADAM-W or like any optimizer from the PyTorch library. Here, the basic logger in our case is a NeuroMANCER class that allows you to have control over the verbosity of your training or over the logging of the parameter values or the results or some artifacts like videos or plots. The trainer is, again, our custom class that takes in the problem class. And this will be the forward and backward for differentiating the computation graph. And you provide with 3 data sets that are PyTorch data loaders with NeuroMANCER dictionary type data sets, where each variable has its key and is mapped to the tensor values. So that's happening under the hood in the trainer. You provide PyTorch optimizer, and then you come up with some hyperparameters for early stopping. You can also go to the trainer class itself and see the definitions for each of those arguments, and there are more that you need not to worry really at this point if you are not a developer or if you are not interested in some hyperparameter optimization. And you can also have control over what is your evaluation metric, what is your training metric, development and test metric. And once you have all of this done, you just do trainer.train, and it performs the optimization on the problem and updates the trainable parameters in the problem itself. So once this is done, I'm now going to run this in my interactive console. Should take a couple of seconds to train this simple system. You shall obtain some visualization of the trajectory. So what you can see over here is the rollout over like 400 time steps, where the red trajectory is the ground truth and the solid trajectory is the ground truth, and the dashed trajectory is the predicted trajectory. And UVC is almost perfect match. They start to little bit diverge at the end. The reason is this is a simple problem, and we are providing the OD structure, so you are essentially learning one parameter. So very simple training task. And the plotting is executed in here, in this part of the code, where we are using NeuroMANCER simulation classes that basically act as wrappers for arbitrary callables. So we can jointly simulate classes from the NeuroMANCER or from other sources like SciPy library or wrapper of the third-party dynamics like OpenAI Gym to facilitate benchmarking and with heterogeneous pipelines. So I'm not going to go into these details of the simulators in NeuroMANCER. There will be separate tutorial, but essentially what happens that we are creating separate computational graph that takes the data set, does the rollout on our NeuroMANCER digital twin and on a ground truth model, and it allows us to compare these trajectories. So that would be everything from this introductory example on the system identification. Oops. And if you have any further questions, I'm going to derail you to our READMEs, our examples, where you can learn more about internal mechanics of each individual classes. You can inspect the APIs of the classes that are used in building the system ID examples. And if you are interested in some research, you can check our papers that use NeuroMANCER to generate the results. So thank you very much for your attention and spending time with me. See you in the next tutorial.